Namaskar students. In this video, we will discuss about Lagrange's method of undetermined multipliers. This method is used when we have to find maxima and minima of any function subject to one or two constraints. Let us discuss the working rule of Lagrange's method of undetermined multipliers. Suppose we have to find maxima and minima. It may be maxima, the problem may be of maxima or minima of a function of three variables. Of a function of three variables. We are considering here a function, and the function is of three variables. Say u is a function, we are representing it by f, and the three variables are x, y, z. This is the function which we have to maximize or minimize, and it is subjected to some conditions, some constraints, and let us take firstly only one constraint, subject to the constraint which is given by this equation, this one. So let us name this equation, this relation which is given between x, y, and z as equation number 1. So what is our working rule? For finding here the critical points, we will be defining a new function, and let us name that new function as, say, h. Let us consider a new function, say h, as we will be defining this function with this function u, which is actually f, plus then we have lambda, and then we will be using this condition, this function g which is present in the condition, this. So we have defined a new function, we have named it as h, and here this lambda is Lagrange's multiplier. Let us name this equation as equation 2. Here this lambda is known as Lagrange's multiplier, and it is non-zero. Now the stationary points of this new function which we have defined, h, will be given by the equations. The stationary points or you can say the critical points, the stationary points of function h are given by del h by del x, partial derivative of h with respect to x, equal to 0. Then partial derivative of h with respect to y, this will be considered as 0. And the partial derivative of h with respect to z, this is also 0. So critical points of this new function h will be obtained by considering these three partial derivatives as 0. And if we talk about these partial derivatives, what will be the expression for this del h by del x? If we see back here, this equation 2, then h is defined in this way. So if we are finding the partial derivative of h with respect to x, it will be del f by del x plus lambda, because lambda is here Lagrange's multiplier, which is free from x by z. And then in product, we will be having del g by del x. So what we will get here, that is del f by del x plus lambda del g by del x equal to 0. By considering the second one, del h upon del y equal to 0, we will get del f upon del y plus lambda del g by del y equal to 0. And by considering this third partial derivative, del h upon del z, we will get del f by del z plus lambda del g by del z equal to 0. So we have three equations. Let us name these equations as 2, 3, and 4. Solving these equations, it will be 3 because we have already named equation 2. So let us rename these as, this is 3, this equation as 4, and this equation as 5. This is our third equation, this is our fourth equation, and this is our fifth equation. So with the help of equations 3, 4, 5 and this constraint, which is equation 2, so with the help of these four equations, we will be evaluating the stationary points for the function which is u. So in this way, we will be applying this Lagrange's method of undetermined multipliers. This method has one limitation, that with this we can find out the stationary points, but we cannot find the nature of those stationary points. So this is one limitation of this method. So let us take problems based on this method, because it will help us in better understanding of this concept. So let us consider first question. The problem is, find the minimum value. We have to find out the minimum value. Find the minimum value of x square plus y square plus z square, given that ax plus by plus cz equal to p. So this is our question. We have to find here the minimum value of this function. It is very clear that the function is a function of three variables. It is involving here x, y, and z. And the condition which is given is ax plus by plus cz is equal to p. So this is our function u. If I compare it with the notations which we have discussed or which we have considered right now, this is our function u, which we have to minimize. And here g is ax plus by plus cz minus p. If I take this p on the left hand side to make the right hand side as 0, then in that case g will be ax plus by plus cz minus p equal to 0. Now see here, we have only one condition, but we might get some problems in which there will be two conditions. So if we have two conditions, in that case, when we will be defining this function h, we will be considering true Lagrange's multipliers. And suppose if we have one more condition, say it is, we are denoting that condition by w xyz equal to 0. In that case, if I talk about this h, what will be changed in this h? This h will be f, which we have already here. Then one Lagrange's multiplier, which is lambda. G is here for the first condition. And then we will be considering one more Lagrange's multiplier, let it be mu. And then we will be having this w, which is present in our second condition. So here this term will be added. Mu is Lagrange's multiplier, and this w is from the second condition. As the form of h has changed, so similarly here these equations will also change. There will be one more terms in all of these three equations. So that will be the change if two conditions are given. So let us come back to our problem. So we have f, let us take this as f, this one, which we have to minimize, and it is subject to ax plus by plus cz. Let us take this p on the left hand side, p equal to 0. Let g is equal to ax plus by plus cz minus p, that is g, which is function of x, y, z, equal to 0. So we have, let us name this as equation 1 and this as equation 2. Now let us define the function h. Consider h as f plus Lagrange's multiplier lambda, and g, that is h is equal to, let us put here f and g, x square plus y square plus z square, this is function f, plus lambda, and let us put this function g, which is ax plus by plus cz minus p. And let us name this equation as equation 3. The stationary or critical points, the stationary points of h are given by del h by del x equal to 0, del h by del y equal to 0, and del h by del z equal to 0. So let us evaluate all these three derivatives and put it in these equations. That is del h by del x. We have h in equation 3rd. So if we evaluate del h by del x, we will get 2x. From y square and z square, we will be getting 0 when we will be differentiating partially with respect to x. and from this we will be getting lambda, we'll be getting a, and all other terms will give us 0. So this will be equal to 0. Second equation which we'll be getting by differentiating h partially with respect to y and then equating it to 0 will be 2y plus lambda b equal to 0. Let us name this as equation 4, this as equation 5, and when we will be considering this third partial derivative, which is with respect to z, we will get 2z plus lambda c equal to 0, and let us name this equation as equation 6. Now, with the help of this equation 2, and with the help of this equation 4, this equation 5, then equation 6, we will be finding the point, and with the help of that point, we will be finding the minimum value of the function f. So if we see this equation 4, from equation 4, we can find out x. And similarly, from equation 5, we can find out y. And from equation 6, we can find out z. But all these x, y, and z, they will be in terms of lambda. So from equations 4, 5, and 6, we get x as minus lambda a by 2, y as minus lambda b by 2, and from equation 6, we have z as minus lambda c by 2. Now, if we put x, y, z in our equation 2, because we have already used 4th, 5th, and 6th equation, now we are left with this equation 2. If you put here x, y, z, and all are in the terms of lambda, then with the help of this equation 2, we can find the Lagrange's multiplier lambda. And once we have Lagrange's multiplier lambda, then by putting lambda in these equations, we can evaluate x, y, and z. So putting x equal to minus lambda a by 2, y equal to minus lambda b by 2, and z equal to minus lambda c by 2 in equation 2, we have ax, equation 2 is ax plus by plus cz minus p equal to 0. Lambda by 2 is common in first three terms, so we can take lambda by 2. In fact, we can take minus lambda by 2 as common, and we will be left with a square plus b square plus c square minus p equal to 0. That is lambda will be equal to, we will get Lagrange's multiplier. It will be with negative sign, minus 2p a square plus b square plus c square. We have just simplified it and we have obtained the value of lambda. Now once we have lambda, we can find out x, y and z. This implies, what will be our x? X was minus lambda a by 2. Let us put lambda here. 2 will cancel out and we will get x as ap divided by a square plus b square plus c square. And y will be bp a square plus b square plus c square, and z we will be putting here in this result Lagrange's multiplier lambda. So we will get z as cp a square plus b square plus c square. So this is the point where h will be having maximum or minimum value, and hence this will also be the critical point for the function f. So once we have critical point, let us find out the minimum value. Minimum value of x square plus y square plus z square, it will be equal to p square. We can take p square common because it will be present in all these three, x square, y square, z square, and we can take this also common because the denominator will also be same, and we will be left with a square plus b square plus c square, and it will simplify to p square upon a square plus b square plus c square. So the minimum value of x square plus y square plus z square is p square whole divided by a square plus b square plus c square. This will be our answer. We will be taking one more problem in our next video.